So let's try into the same game now for the fermions. So look at the algebra of fermionic operators. So let AI and AI vector, where then I is some discrete value to a finite value, but can be readily extended to infinite number or to continuous variable, be fermionic Fock space operators. Now obeying the fermionic operators algebra, meaning that AI and AJ dagger to anti-commute. So the plus here stands for the anti-commutator, and then you get annihilation operators and creation operators themselves, just all anti-commute. And that's just again, so what we are after is eigenstates of the annihilation and creation operators to construct the path integral. So let's search for eigenstates of the annihilation and creation operators. Well, the first observation is if we again look at eigenstates of the creation operator, then I mean just see applying the same argument as before, so that didn't rely on the commutation relations. Just again, if there was an eigenstate of the creation operator, then what we could do, we could write this general eigenstate as a linear combination of a given Fock space, state base. That is, we could write it as some linear combination of states which contain certain numbers of particles. There would be a minimal number of particles, and this is not left invariant under action of the creation operators, so they do not exist. Now, what about the eigenstates of the annihilation operators? Well, again, the argument that eigenstates of creation operators do not exist does not apply for eigenstates of the annihilation operators if we allow for linear combinations containing arbitrary numbers of particles. But there is one peculiarity of the eigenstates of annihilation operators of a fermionic algebra, and this is what we are going to see now. So let's assume there is a Fock space vector which we now call eta, such that operating with annihilation operator on eta just gives you eigenvalue, which I call here eta I, and this for all I. So this would be the equivalent of what was written for the bosonic coherent state. So let's assume that we find such a vector eta, which is simultaneous eigenvector of all the annihilation operators with an eigenvalue eta I. Well then, so we're here, the eta I is the eigenvalue of annihilation operator. Then just applying the bosonic, the fermionic commutation relations, anti-commutation relations, it follows from commutation relations that if I act first with the annihilation operator aj and then with ai on eta, this should give me, because they anti-commute, the negative of operating in the reversed order. Okay, so this is just using the fermionic anti-commutation relations. But then, if this is an eigenstate of all the annihilation operators, it immediately follows that this would give us an eta j, and this would give us an eta I times this vector, and this would give us just the opposite. I mean, the reverse order. So it would immediately follow this relation for the eigenvalues of the annihilation operator. And this clearly tells us that, well, these eta can't be just real numbers because they have to invert sign if I commute them. Okay? So they have to be anti-commutative numbers. So if we allow for the concept of eigenstates of fermionic annihilation operators, we are forced to the concept that the eigenvalues of these operators have to anti-commute. And this means that to make sense of eigenstates of the fermionic annihilation operator, so if we want to talk about fermionic coherent states, we have to generalize our concepts of number. Okay, so generally we talk about number, real, complex, or whatever numbers, but they all commute. So we have to generalize this concept of numbers, and this then leads to the concept of Grassmann algebras. Okay, so we have to generalize the concept of numbers to Grassmann algebras. Then, once we have done this, we can see that we can understand the coherent states for fermions as being some linear combination as before of creation operators where the eigenvalues or the parameters that parameterize equilibrium states are now not drawn from normal numbers, let's say complex numbers, but are drawn from this Grassmann algebra. Now I'm like a little bit in a situation where I don't really know how to proceed, because like normally I would now explain like Grassmann numbers and whatever, but I think this, as I understood, like all of you know or have already encountered Grassmann numbers. So I will just try to review some things, and okay, it might be that you're bored. Okay, let's just say, I mean, this is now where we help. Like, I will just like go like how I prepared, reviewing some things. If you say, well, that's clear, I can accelerate. If you don't understand something, then you have to ask. Okay? Because I mean, if one doesn't understand what Grassmann numbers are, I mean, all examples that we will discuss after having introduced the function integral will be related to fermions, electrons in the metal. So if you don't understand like what is going on with Grassmann numbers, there's no way you will, I mean, this will be of any use for you. So please ask, and as said, there will be also some exercises. So so let's see. So let's just make some excursion to Grassmann algebras. Just to, I mean, as I understood, for you just to recall some things. And I mean, all that I'm always doing here is not really, I mean, let's say, not interested so much in the mathematics. So we don't go into mathematical details and sharp definitions and whatever, but we just take some constructive point of view, that we see like how they appear and how to construct the Grassmann algebras and how to work with them. So just one comment. So so far we have always dealt with numbers. So what are numbers? Numbers are, like in mathematics, would be some field, which means that you have a set of elements and you have defined two operations on the set of elements, which is addition and multiplication. And these elements, or these operations, are operations which take two elements from the set, make something with them, and map them again to the set. Okay? And there is a certain number of rules that these two elements have to satisfy, so multiplication and addition. Now, of course, if you want to generalize the concept of numbers to Grassmann algebra, you have to give up some of these rules of the games which define the field, because otherwise I mean, we would end up with a field. So what we are going to give up is the idea of communication, okay? But we will keep like ideas of associativity and all this. Now, what you can then think of is, let's think of the Grassmann algebra as again a set of elements, and you have mappings from the set of elements, which takes two elements and maps this again to the set of elements. And we have again two operations. We have an addition and we have multiplication. And to make it like, to see how it works, we will just construct the Grassmann algebra. But we can already like say what we start out from. So what we will start out from is a vector space. Okay? In a vector space, what do you have? You have a set of elements, which are the vectors, and you know how to add vectors, and you have some scalar multiplication. Okay? So let's start out with a structure that we have from a vector space, and just define on this space now the one thing that you still want to have, which is multiplication. And this multiplication will be such that it's anti-commutative. And actually, I guess most of you already know exactly this construction. This is the exterior algebra of wedge products. So this is exactly what you do. Now you have like the vector space of forms, and this is the vector space, and you define some multiplication on this, which is the wedge product, and this is anti-commutative. So this is the realization of the Grassmann algebra. And we are just exactly, reviewing these concepts, and this is like how we think about them. Okay, so this is a very, let's say, constructive way to look at it. So, so this is Grassmann algebra, and we just state the construction, because this is like what we need. This is how it will appear. Let's denote the Grassmann algebra with some A. So the way how to construct our Grassmann algebra is to start out with some elements. I did take a finite set of elements. Which I call the Li. I goes from 1 to n. So this is n elements, and these are defined the elements of a Grassmann algebra. Actually, they are called the generators, and they are called the generators because once we have defined the set of elements, we can just use them to now construct all the A. Okay? So why do we start out in this constructive way? Because we saw that if we want to allow for coherent states for fermions, we are forced to such numbers eta I, which anti-commute, and which will be the eigenvalues of the fermionic annihilation operators. So in all our applications, this set of generators of the Grassmann algebra will be just, the numbers or the Grassmann numbers that are used in the construction of the coherent states for the fermions. Okay. So let's start out from these n sets, which we just give a name, which we call generators, and now we impose two rules. And if you like, you can think of these just like the one forms. Let's say dx, dy, dz in R3, okay? It's like, so we impose two rules, which are first, the elements eta I can be added and multiplied by complex numbers. Okay. So we can write any let's say, linear combination. And this is again in the algebra. So this in a way will define us the vector space. Now we allow here still also a component which is not multiplied to any of the element of the generator. So we add, let's say, a unit element which is just from complex numbers. Okay? We call any of this linear combination will be in the algebra. Okay? So this is in a way defining a vector space, and we still have here something proportional to it. Then the second rule is now the multiplication. Which is the rule that generators can be multiplied that is, we define a product which is a mapping of two elements of the algebra. We take two elements of the algebra and map them onto, we take such two elements and just find this. And now we put the rules for this multiplication. We say that the rules are that this product is associative and anti-commutative. So let's write our formula. So if we take three such elements, we can make the multiplication first these two and then multiply the result with the third, or we can just first multiply these two and take the result and multiply this with this. So this would be the associativity. And the anti-commutativity, well, this is that the product is a minus would be applied in the other way. Okay, so this is actually what you know from the exterior algebra, no? So there we would, let's say, define dx, dy, dz. We would now say you can write any element like something proportional to unity, or dx, dy, dz. And then we say that for the generators dx, dy, dz, well, we have associativity, and we have, let's say, dx badge dy is minus dy dx. You can always think about this, just the same. So now that we have defined these two rules, then we can say that we can now generate the entire algebra. This is why they're called the generators. So with 1 and 2, we can form the set of all linear combinations of the form we have a constant, and then we can have n products where small n goes from 1 actually to infinity, we can be right, and what we use is E1, E2 up to En. And these can go from 1 to n, and we have coefficients E1, E2, En, and then have here the product of E1, E2, and En, where again these coefficients C are just drawn from the complex numbers E1, E2, En, complex numbers. Okay, so this would be just writing maybe in some abstract way. So just writing the general linear combinations that you can form by products of the etas. Okay, so this could be C0, then there could be just, let's say, C1 eta 1, then there can be C3 times 3 C3, 5 kind of adder 3, adder 5, and so on. Okay? Just have defined that there's a product there, and we can then consider all linear combinations. Okay? So we can, in this way, with the edas now generate all linear combinations, which then will define mathematically something which is as a structure of a finite dimensional algebra. Okay. And it's called the Grassmann algebra. Grassmann algebra, and the elements are in this algebra called Grassmann numbers. So the elements are called Grassmann numbers. Actually, it's not really numbers, so some may prefer to call them Grassmann variables. Okay, so this is like a very constructive way to look at it, and this is exactly the way how it will appear. Yeah, we will introduce a set like elements at I, just being the eigenvalues of the creation of the annihilation operators AI, and then in our entire, so then you can define the coherent fermionic coherent states as exponentials of these Grassmann variables, and these variables will appear then in the functional integral. So, and we just in the end have to know that we can multiply them in the anti-commute, and we can multiply them with complex numbers. And there's some comments I have to say here, just for the rules again. So, the one thing that you can always use is that the generators, eta I, and complex numbers, they commute. Element C commute. Okay, so the way you can define here some, let's say, grading. So you have those which do not have any Grassmann variables or generators. Here are the terms proportional to generators. Now, if we use here the general linear combinations to generate the entire algebra, the next like order would be that we have products of 2 elements and we have products of 3 elements and so on. So actually this means that if you take here, so this is more general, if you take elements from the even set where you have no Grassmann generators or 2 or 4, they will always commute with the others, okay? So let's write this more general. General Grassmann numbers made of even products of generators eta I commute with arbitrary elements from the algebra. And actually this just, I mean, so we are forced to introduce the Grassmann variables or the Grassmann generators, like the eigenvalues of the fermionic emulation operators, because of physics, I mean, because of the anti-combination relations. So the numbers should then, of course, reflect all the physics of fermions. And this statement actually just tells us, well, if you take two fermions, let's say, or an even number of fermions, they just behave as bosons. Okay? This is just like the physical way of saying this. Now, in the same way, if we take a generator which with itself, well, it has to anti-commute, and this is therefore zero. So again, this is mathematical, but this just reflects the physics of fermions, so this is just a Pauli principle. Okay, so we see that, I mean, indeed we encounter all the properties of fermions in this algebra, so it should be, I mean, as of course it should be. Now, again, like, I think most of you are familiar with already one Grassmann algebra, which is just the exterior algebra of forms. So now that we have defined like the object, so this is generalizing numbers, this is now the Grassmann algebra, which we have to deal with, we have to deal with Grassmann numbers when talking about coherent state path integrals for fermions, but we still have to know how to work with them. So we have to know how to calculate these Grassmann numbers. So this is all fine. I will just briefly summarize like what would be functions of Grassmann numbers, how to differentiate them, how to integrate them. And then we would be done with this, and then next time we can really start with the construction. Is this okay? So the speed is fine? Yeah? So you recognize like the Grassmann numbers that you know? Okay. And in the end, I mean, it's really just like complex numbers, like just using them one gets at some point, they are just getting familiar, and I mean, yeah, this has always to apply this kind of concept, which might be strange in the beginning. So actually, I mean, if you calculate with Grassmann variables, it turns out that you might first think, oh, well, this is all very complicated, but in the end, all calculations are typically much easier with Grassmann elements than with bosons and or with normal C numbers. And some examples I think we can see. So let's just summarize here some calculation properties, calculation with Grassmann numbers. So we always start out, say, with some set of generators. So let these either I be the generators of the Grassmann algebra. So the first thing that we want to define is functions of Grassmann numbers. And again, I'm going to just give like the rules or recipes because in the end we just want to know how to apply them. So the functions of Grassmann variables are actually just defined via the Taylor expansion of the function, okay? So they are defined. So you start out from some function f, which has, I mean, all the properties that you need to make a Taylor expansion. And then we define, make it very general, function, multiple function of Grassmann variables as just raising from general Taylor expansion, so I is 2 blah blah okay, we go from 1 to n. Okay, all c equals to 0, and then you multiply this I. Okay, so this is maybe, I mean, not so easy to see, to read, but it's just this, the normal Taylor expansion of a multi-valued function, okay? So to make it, maybe give an example, let's take, so you start from some function and now want to see what is the function defined for Grassmann variables. So let's just make one example that we have like the Grassmann algebra defined by one generator, okay? So let's take the function, the exponential function, and let's say x of either. So the exponential function is defined via the Taylor expansion, so this we can write as a Taylor expansion, and then we see, well, if we just look at it, the first element, well, is k equals 0 is 1, then we have k equal 1 would be the either. Now the next element would be 2½ either squared, but there we see, oh, okay, it already stops because the anti-commute by Pauli principle, either squared is 0. So we see that, for example, if we have just one variable, the exponential of the Grassmann element is just 1 plus either. It's just finite term. And if you have here a finite number of generators, this turns out, I mean, you can think about it and you will see, well, it will always have to stop at some end. So you can always think of functions of Grassmann variables just as some finite polynomials. Yeah.
But in this construction, I have to consider that the derivative operator acts just like the usual.
Yes. This is just, yeah. So you can think like, if you like, in a different way, just think as the f already as some Taylor, defined by some Taylor series, and then insert the elements of the Grassmann algebra instead of real numbers. And that's, so this is, I mean, already. You can already see that many things can become much easier. Okay, so this would be the functions, and yeah. There's also some, I will distribute afterwards in the exercise sheet. So this is just getting familiar, and yeah. Now, or questions, or clear, or? So just think of polynomials. Now differentiation, so that we have defined differentiation functions, we can now talk about differentiation. And there again we just define the rules. So this is differentiation of, or with respect to Grassmann variables. Grassmann variables. So we just define the rules. So we define that the derivative with respect, so this is again, I use this kind of short notation for like this, for derivatives. I'll find it more this is defined on the generators as just giving you a Kronecker delta equation. Okay? So that's the definition. So the derivative of the exponential with respect to either would then be just 1. Now, defined in this way, we can see that actually the derivative itself has to anti-commute with the generators. Yeah? And this can be seen. So notice to be consistent. So these must anti-commute themselves, so this must itself be an anti-commutative element. Just to give you an example, so if you would take del eta I times eta j eta I, so this is now, I mean, you have to be careful because I mean these anti-commute, okay? So we have del, the derivative with respect to eta I, operating on eta j eta I. Now to calculate this, what would we do? We will first use the anti-commute to have then the eta I close next to the derivative. And there we know how it operates, so it gives us a 1. And then we have here the minus eta j, okay? So another way to do it would be just to use that the derivative anti-commutes with the eta j, to put it here, and then we get the same, okay? So we see that to make it consistent, the anti-commutation relation between the generators implies that the derivative and the generator themselves have to anti-commute also, okay? And again, so whoever like did not calculate with this kind of things and it's like it's just getting used to it. At first, like when I saw it, I didn't really know what is going on. But then if you go through the exercise sheet, then, I mean, you get used to it.
So this differentiation is not the same that the one in the Taylor expansion?
No. So this is here the Taylor expansion of the function. Let's see if it's the same. So I would have to think if it might turn out the same, I can't say. So here I just really think always about the series expansion where you then put in, I guess it will turn out the same. Because in the end, I mean, this is also what, I mean, yeah. Yeah, I think if you just apply it, but I'll confirm. Okay, so this is the differentiation, and here, I think, I mean, the best way just to think of polynomials here, and if you want to see the function of some eta, just always think about the Taylor's, about the series representation. I mean. So the final thing that we want to do is integration, and then I still state the coherent state, and then we are done. Okay. Again, just, I mean, this. One really should do some exercise. So the integration then also is much, let's say, easier and better behaved than for Grassmann variables than for normal complex numbers. So the integration we again introduce by defining the following, that we say the Grassmann integral over, say, some complex number, which here would be 1, it's just 0, okay? But the integral of the generator is 1, okay? And this is the definition. And to see how this works, we can now use, I mean, again, an example where we define the integral, or where we look at the integral of a function. Okay, so it's just a definition. And let's look at an example where we have the Grassmann integral of some function of a Grassmann variable. Well, then we say what we said before, the function of the Grassmann variable is defined via the Taylor expansion. Now, in this case, again, because we have just a single variable, this stops after the first term, so there's no other terms because. And now we apply the rule, so this would be just 0, okay? And this here is a C number that commutes with this here, and this gives us 1. So this gives us just the derivative of the function 0. So actually we see that what this gives you is the same as what one would get if one would look at the derivative of the function. This you might check that using the definition of the derivative and just using the same game, so using the derivative operator here on the function, you again represent this as a Taylor expansion, you will see that's the same. So derivative and differentiation and integration is the same. And now a very important property for us is that if you look at integrals of Grassmann variables, they are always finite. You never have to be scared about convergence or anything. Yeah? So they are all finite. And then I don't know if it's on the sheet. Grassmann integrals. Yes, it's on the sheet. So we have, I mean, in the end, we saw that in the path integral, all what we were always interested in, or what we really needed in the end, were Gaussian integrals in the path integral. No. So one important property that we use is that the Gaussian integral of some factor a gives you 1 over square root a. So if you generalize it to some symmetric form, integral over symmetric form, it gives you 1 over square root determinant of a. Now, if you look at the corresponding Grassmann integrals, you see that instead of looking, let's say, symmetric forms of complex numbers, but of Grassmann variables, you will get, instead of 1 over the determinant, you get the determinant. So this is a property that I think you should look at in the exercise sheet, which is very interesting because in a way they behave opposite to each other. So the complex number integrals gives you like 1 over determinants, and the Grassmann gives you determinants. And this is often used like to start out from normalized partitions functions or whatever. So if you start from a problem where you want to have a normalized partition function, you can always achieve this by introducing the opposite degree of freedom. So if you have dealing with bosonic and Grassmann variables, you can always start out from something which is normalized. And this is like supersymmetry appears in condensed matter, for example. So this is like the things that I just stated and that may be weird and not, I mean, so, yeah, not so easy to get first, but one gets used to it. So this is the key here is just doing exercises. So this is why we have the sheet, and then I just give now the definition of the coherent, of the fermionic coherent state and some properties, and with these properties we can then next look at the construction of the path integral. So this takes like 5 minutes now. Okay? So you know already Grassmann variables, but did you already calculate with them? I mean, did you look at functions of Grassmann variables, derivatives, and integrals, or is this new? This is new? Huh?
Not for me.
It's not new for you. Okay, so it's okay. Okay, so okay.
Another classes, but not.
Okay. Okay, so did you ever? It's new. So I mean, what?
I have some intuition about that definition of the integrals, because that I already saw this before, but that's not natural. I don't know.
Why you define it this way?
Yeah, because you could define it another way and get different results. I think.
No, I think so. You have to. So you have to have some properties of the integral, which actually fixes this. So you have to have. I recall like very vague memories. Like it has to be. There's some properties which I guess fixes this.
Why you require some kind of fundamental calculus theory, you know?
The frequency of the integral.
Yes.
No, yeah, so you can like if I look it up, but you have some like invariance properties under redefinition of variables, like and these kind of things. If you use them as a definition, then you will end up with this.
Mm-hmm.
I recall this vaguely,
Yes,
but I have to look it up.
I already saw this kind of argument. I don't know. I remember that.
Yeah.
You translate the.
Exactly. So you can translate and all this, and it shouldn't vary. Yeah.
Even though this was not the.
Yeah. That's not spectrum.
This is not convincing.
Yeah. So I remember that I once looked at this and I forgot it. I look at it and then we can discuss it. Yeah.
Okay.
Yeah. So okay, just now with all this, we just did to get some sense to what is the eigenstates of the annihilation operators, so fermionic annihilation operators. Now we can define states which are linear combinations of infinite, like states which contain infinite numbers of particles. So we have again the exponential. This is now a fermionic creation operator. This acts again on the vacuum where you don't have any states around, and these now are the Grassmann variables. Okay, so you have again here a short notation for the set of all eta I to eta n, and this defines the fermionic coherent states. So just here, so the eta on the left hand side is the short notation for all the eta I n set of. So these will define our Grassmann generators with which one then constructs the Grassmann algebra. And what is an exercise is that if you define them this way, they are eigenfunctions. And I think, the best is to look just at one variable first. So not at n different variables. So they are eigenfunctions, simultaneous eigenfunctions of all the fermionic annihilation operators in the sense that they fulfill this equation here. And actually, if you go through the proof for the bosons and the fermions, you will see that here, for example, the calculation for the fermions is much easier. Because in the proof of the bosons, well, you expand this infinite Taylor series, power series, and then you have to look at all the commutation relations and so on. But for fermions, this stops at some point, and it's all easier. So you can see this. Now, there's one thing that I should still one piece of information which is missing, and this is so far we only talked about the generators or the elements of the Grassmann algebra. Now we connect them with the elements which, with the creation and annihilation operators. So we should define here still, or we should say that Grassmann generators, again for consistency, have to anti-commute with the fermionic operators. Okay, so this is so eta I aj equals minus aj eta I. Okay? And these are fermionic coherent states. And now I just write down a couple of properties similar as for the bosonic case, and this is most of them are on the exercise sheet. So let's see. So the properties of bosonic coherent states. So the coherent state is defined as either exponential of Legge acting on the vacuum. Okay, so just you can write it this or this way, just using that computation. Now, if you look at the adjoint vector, this is use again the anti-commutation to write this is exponent of theta I ai. Okay? So there's one very important remark here, and this is that these eta I and these, or these eta I bar and these eta I, they are completely independent variables. Okay? There's not something like a complex conjugation of Grassmann variables. This is what Grassmann generates. This is completely independent variable from this one. Okay? So there's no relation between. So the adjoint generate where adjoint generators eta I. Just define goods over bar to make, the analogy with complex numbers, are not related in any way to, eta I are completely independent variables. Completely independent variables. Okay. Now we can ask again about derivatives. We'll just write down four more properties, and then we're done. So first we have, one can ask what is if I operate with a creation operator, and this gives you a derivative. Then one can use again the complex conjugate, or the adjoint of this equation to find this relation, and so this is two relations, and then for the construction of the path integral, one again has to use the overlap of coherent states is finite. So here it's given by exponential of here the product of these Grassmann variables. Okay, and this means again that as in the bosonic case, the coherent states can be used to generate a unit operator in Fock space, but you have to take into account, due to the finite overlap, these states are over complete. So you have a finite overlap, and then for the construction. Next time we will extensively use the one operator in Fock space. Can be written as this multiple integral. Now integration over the two independent variables eta bar and eta. This exponential again takes into account the finite overlap between them. And then we have here the projection. So this is again the over-completeness over because of the finite overlap. Apart from that, we have a complete set which allows us to represent the unit operator, and which then will be the basis to construct the path integral for fermions. Okay? So this is this. And then here's the exercise sheet. So okay, so next time we construct the path integral, and then let's see how far you get with the exercise, and maybe we make one, instead of the lesson we discuss the exercises, and maybe one already small application of the function integral, and then we start with some examples.